So, this is Mr. McMurray on this bright and cheery Thursday morning, all right? And we're going to get after it here, talk about some momentum. All right. And we are going to get the momentum going here. We're talking about impulse-momentum relationship. Last time we talked about impulse and said it's the amount of force times the length of time that you apply it. And so the more force and the longer you apply it, the more it's going to change the momentum. All right, because impulse is the force and time that changes the momentum. All right, changes its speed primarily. All right, and therefore its acceleration, velocity, acceleration, etc. All right, so the impulse-momentum relationship. Well, here's the deal. All right, if we look at some things that we know about this, we know, first of all, that the formula for, according to Newton's second law, we usually solve it for acceleration is equal to force over mass. But if we solve it for force, the force is equal to mass times acceleration. Okay, now acceleration is how much the velocity changes over time. So if we substitute delta V, change in velocity, over time for acceleration right here, we would get this formula. Net force is equal to mass times the change in velocity over time. Okay, and that would still be the same formula. All right. Now, if we get rid of the fraction, like we usually do, we would multiply both sides by t. T times t would cancel, and this would be force times t, and we would end up with this formula. The net force times time is equal to mass times the change in velocity. All right. Now, we have seen both of these before. Net force times time is the formula for impulse, and the mass times the change in velocity is the formula for change in momentum. What is this saying? The impulse is exactly equal to how much the momentum changes. Okay? And if you remember right up here, we said mass times velocity, or change in velocity, is going to give us kilograms times meters per second. Then that's the same units we would have in force, which would be Newton seconds, or if you simplify it, it would be kilograms times meters per second. So they are measured in the same units. Why? Because they are equal to each other. And so we can say that the impulse is equal to the change in momentum. Not the momentum, but the change in momentum. And that's what usually trips people up. Okay? So the formula here, force times the change in time, or delta t, equals the mass times the change in velocity. All right? And basically that's what we're saying, is that the impulse, the amount of impulse, is going to be equal to how much the momentum of the object changes. Okay, more about that later on the worksheet, and we'll talk about more in detail what that kind of means. But for now, let's just accept that and move on. All right, now let's look at some interactions between impulse and changes in momentum. How can we use the impulse to change the momentum? Well, one of the ways we like to do that is to increase the momentum. We want more momentum. We want momentum. All right. Sorry, didn't have that. Momentum. All right, so we can increase the momentum by, we talked about this a little bit yesterday, we can either increase the amount of force that we apply, or we can apply it for a longer time, or we can do both. Also, if you want to decrease the momentum, you could decrease the force, decrease the time, or decrease both. Okay, now, some examples of that. There are cannons that are more long range, okay? Or you can compare a pistol versus a rifle, and basically these long-range cannons, or a rifle, for example, will have longer barrels, okay? So if you take a rifle and compare it to a pistol, all right? Now let's just say this is a 22 rifle and this is a 22 pistol. They shoot exactly the same bullet, okay? They have exactly the same amount of gunpowder. When it goes off, there's exactly the same amount of force, okay? Now the force is caused by exploding, heating up gases. All right, and so basically when it explodes, those exploding gases are going to push the bullet one direction, but we know Newton's third law, every action force has an equal opposite. It's going to push the bullet one direction, it's going to push the gun back the other direction. Okay, now the only time that as long as it's inside the barrel, that gas is trapped behind it and pushes the bullet out to the end. But if you look at a pistol, same force acting on the pistol, same force acting on the bullet, and as long as it's in the barrel, the expanding gases are going to push it out. But once it gets to the edge here, the gases can start going in other directions and they quit pushing the bullet. All right. So the time that the force is applied is the time that the bullet is in the barrel. Well, in the rifle, it's in the barrel a lot longer, so the force is applied a lot longer. And so you get a lot more force if you shoot a rifle than you do a pistol. You see in the old movies, hero pulls out his gun, shoots someone off the opposite canyon or something with a pistol. Well, the odds are no, probably not. Okay, pistols don't have as much force and aren't as accurate. As they go farther, they're going to poop out. Okay, if you want to do a long-range shot, you need a rifle with sights on it. All right, and you're still going to have to adjust up or down. If they're far enough away, you're going to have to just shoot a little higher so that gravity pulls it down as it goes across there. But still, you're going to get a lot more force on it with the barrel. If you have longer range cannons, then you're also going to have longer barrels. Same reason. It's going to apply the force longer. So the longer the barrel, the longer time that the forces are acting on the bullet, cannonball, whatever. Okay, whatever kind of projectile you're trying to shoot at to kill people and do damage and all that kind of good stuff. Okay, and so basically by increasing the barrel, we've increased the amount of time that the forces act on it. All right, and therefore we're going to get more momentum change. All right, and therefore more impulse. All right, now we talked a little bit yesterday, follow through. Anytime you swing something, you may not be able to see that because it's kind of behind me, but yeah, down here you see some famous tennis player hitting the ball here. I don't know my tennis players nowadays. I kind of got out of it with McEnroe and a few of those. I still recognize a few names, but not many. All right, so anyhow, if you follow through when you hit it, you will hit the ball, either the bat hitting a baseball or softball, your golf club hitting the golf ball, or your tennis swing will hit the ball for a longer period of time, and therefore you will get more momentum. And that's why coaches are always saying, follow through. You need to follow through, even basketball. Follow through on your shot, okay? All right, so there we go. And, of course, if you're lifting weights, if you can apply more force, then you can get more momentum change or more impulse, okay? And that's why we lift weights, so we can apply more force on the tennis ball or whatever when we do it. All right. Now, something else that we can do sometimes is we want to stop something. If we stop something, say it has a certain amount of momentum, to make it stop, we're going to have to get rid of all that momentum, right? Because the velocity is going to have to be 0, and then that will get rid of its momentum. We may want to change momentum over a long period of time, okay? And this means less force involved, okay? So this has to do with stopping objects. So we want to get rid of all their momentum. We want their momentum change from whatever it is to 0, okay? Now, to do that, let's look at some examples. Okay, we would go outside and we would throw eggs at a sheet, but that won't help much here. All right, say someone gets hit by a punch, okay? They say if you get hit, you're supposed to roll with the punch. What does that mean? You're supposed to roll with it and move the same direction as the punch, okay? Why? Because that increases the amount of time that the force is applied, okay? And since there's going to be the same amount of impulse either way, if we can increase the amount of time that the force is applied, then we're going to decrease the amount of force applied. All right. For example, if you're bungee jumping, hitting a haystack versus a wall, or rolling with a punch, or catching a ball or egg, what does all that mean? Well, let's go to a place where I can draw, and we will talk about that. All right, here we go. And now we got some pictures to think about this. All right, say you have a vehicle, this truck. It has a certain amount of mass, and it's going a certain speed, big velocity, okay? It's going really fast. Now, to bring its momentum to 0, you can do it by running into a haystack, or you can do it by running into a wall, okay? Obviously, you're going to get slightly different results. Why? It takes the same amount of change in momentum. You're going from, say, 60 miles an hour times a ton, so that's 60 mile per hour tons, whatever units you want to call that, okay, 60 units, to 0. So you're going to have to apply an impulse of negative 60. It's going to have to get rid of all that, okay? But here's the deal. If you hit the haystack, it takes a long period of time, and therefore you don't feel very much force, all right? But the force times time is equal to negative 60, so it's going to stop it, and it's going to bring it to a complete stop. Now, when you hit the wall, it's going to do it really, really fast, okay? So the time is tiny. So in order to get enough impulse to stop it, it has to apply a lot of force on the vehicle, okay? And therefore, force is what kills you and wrenches out the vehicle, so you end up dying from this one, okay? So that's the difference. You still have the same amount of impulse, a little force over a long period of time or a big force over small. It's enough to stop it completely, but because you apply it over a long period of time, then you don't feel as much force. Okay, same thing happens with bungee jumping. When you jump, when you reach the end of the rope, you have pretty good speed going on. You got a lot of momentum, but the rope stretches out and slows you down gradually. So it may take, like, say, a second, okay, or maybe a second and a half to slow you down. Now, if you had a chain or something attached to you that didn't give any, you get to the end, and it would yank your ankles right off. Why? Because the time is really, really small, so it has to exert a large force on it to stop you. But if you have the stretchy bungee cord, it takes a long period of time to stop, and so you feel small amount of force. Same amount of impulse, but same total impulse, but you're changing the amount of time or the force. Okay, we talk about a egg. We're going to do a thing at school where we throw an egg against a sheet, and maybe I can get a video of that and put it up for you, but against the sheet. Well, the sheet gives with the egg, and so it spreads out the egg, hitting over a long period of time, and so it doesn't go splat. You throw it against a wall, small amount of time, but a large amount of force, and so it will splat it. Even though the same amount of impulse, total impulse, is going to make a big difference on how much it stops. Okay, if you're catching a ball, if you reach toward the ball, you hit the ball, there's a smaller time of impact if you're moving toward it. On the other hand, if the ball comes to you and you move your hands with it, you increase the amount of time, so there's less force and it's less likely to bounce off your hands. A lot of times in football, you see that someone has to drill the ball really hard, and if the receiver has to reach out for it, it bounces off and he drops it, or it hits him and bounces off. Okay, so, but if you can bring your hands in with it and catch it, you're extending the length of time, and therefore you feel less force, and it's less likely to bounce off and have an incomplete pass. All right, so that kind of covers some how momentum can change over time. Now, let's do the next thing we want to do. Hang on, let me go here. All right, you gotta get there, but I think it'll be faster just to do this and just stop it and do it again. Okay, here we go. All right, so notice that having the same impulse doesn't mean that you have the same force. It doesn't mean you have the same time. It just means the product of the force and time are the same, and that's why it makes a difference whether you do it over a short time or a long period of time. Okay, and I'm going to have to learn to put my pictures in a different spot. Okay, that right there where the camera is not good. Actually, I guess I could move my camera. Okay, there we go. Sorry. Okay, now the last thing I want to talk about is this. Okay, and this is decreasing the momentum over a short time. And this is just the opposite of what we just said. If you decrease the momentum and stop something or apply a force over a short period of time, then it's going to apply more force, okay? If you lean into a punch, then it's going to hit for a short period of time and you feel more force, and it's going to hurt and do more damage to you, okay? We're talking about the egg hitting the wall or the car hitting the wall. It's going to stop you in a short amount of time, so you feel a big amount of force. Okay, that's not good either. Okay, but if you talk about kung fu, when they're breaking things, first of all, notice they don't just break anything. They tend to have things that are fairly brittle, okay, that vibrate and will crack. But also, they have to toughen up their hands. But when they deliver their punch, they don't just go all the way through it. They hit it, and then they bring their hand back up. Why? Because they want to hit for a short amount of time, which means that they deliver a bigger force on the cinder block or wooden block or whatever. Now, once that force is applied, then it sets up vibrations, and since it's usually something fairly rigid, it will shatter and break. Okay, still pretty impressive, but you notice they don't do it on solid steel or something like that. Why? Because it's not going to vibrate or have enough force to break it because it's too hard. So they did pick their surface, but like I said, still very impressive when they do it. All right. That's going to be it for this one right now. We will stop. Time's about out. Run out of momentum, I guess, for now. So just on the impulse, I think I will stop right now because that's how I like doing things on impulse occasionally. Have a great day.